Hello students, after elastic collision, the next thing that we have to study is perfectly inelastic collision, and here we are taking the case of one dimension. So we are going to study about perfectly inelastic collision in one dimension, and it is the case when two colliding bodies stick together and move as a single body with a common velocity after collision, because such type of collision is called perfectly inelastic collision. So we have two bodies collide against each other and stick together and move as a single body with common velocity after the collision. Then such type of collision is called perfectly inelastic collision. Now the situation is, before collision we have two objects, and before collision they have some velocity. This particle m1 has some velocity u1 and m2 is at rest. That means the particle m1 is approaching m2. This is the situation before collision. And after collision they start moving together after sticking together like this, m1 m2, with some common velocity v. V is the common velocity of this whole system of the two bodies. This is the situation after collision, right? So now we know that if there is a collision, either elastic or inelastic, momentum remains conserved in both cases. So first we are applying the law of conservation of momentum. So since linear momentum is conserved, we get linear momentum before collision, that means m1 u1 plus 0 is equal to linear momentum after collision. So after collision the body acts as a single body moving with a same or a common velocity v. That means the equation is m1 u1 is equal to m1 plus m2 into v, and by rearranging this we get the value of v is equal to m1 u1 upon m1 plus m2. So this is the value of v. Now we can find the value for loss in kinetic energy. Since in the case of inelastic collision kinetic energy is not conserved, there is some loss in kinetic energy. So we are going to find the loss in kinetic energy. It implies delta k. Now delta k is the change which representing the loss. That means initial kinetic energy was greater than final kinetic energy. So we have to find loss by applying delta k is equal to ki minus kf, and delta k is equal to half m1 u1 square minus half m1 plus m2 v square. Okay, this is the case. So delta k is equal to half m1 u1 square minus half m1 plus m2, and on the place of v we are going to substitute this value. So it is m1 u1 upon m1 plus m2, right, iska whole square, and delta k is equal to half m1 u1 square minus half m1 plus m2, right, half m1 plus m2, and if we solve it we get m1 square u1 square m1 plus m2 का whole square. So delta k is equal to half m1 u1 square minus half m1 square u1 square upon m1 plus m2, and by taking common half m1 u1 square we get 1 minus m1 upon m1 plus m2. So this is the value of the change or the decrease in kinetic energy or the loss in kinetic energy. Since this is a positive quantity, that means there is some loss of kinetic energy in the form of heat or sound. So kinetic energy get lost in the form loss happen in the form of heat or sound in case of inelastic collision in one dimension. Now if we want to find the ratio of these kinetic energy, initial and final, so the value will be, let's see, the ratio of final kinetic energy to that of initial kinetic energy. In this case we get half m1 plus m2 v square upon half m1 u1 square. It will be equal to m1 plus m2 upon m1 into v square upon u1 square, and on solving this we get m1 plus m2 upon m1 into we can put the value of this v square here. Then by substituting the value of v square we get m1 square u1 square upon m1 plus m2 का whole square, and over to this we have u1 square, right? So the value become m1 plus m2 upon m1 into m1 square upon m1 plus m2 का whole square, and by solving we get kf upon ki is equal to m1 upon m1 plus m2. This is the required value, and since m1 upon m1 plus m2 is less than 1, it shows that kinetic energy, final kinetic energy is less than initial kinetic energy. That means there is some loss of kinetic energy. So this shows that the kinetic energy after collision is less than the kinetic energy before collision. That means there is some loss. Now if the target is massive, if we have massive or a very heavy target, in that case m2 is much greater than m1. So when m2 is much greater than m1, then this quantity is approximately is equal to 0. In the case of massive target, this quantity approximately is equal to 0, and if this is approximately is equal to 0, it implies the final kinetic energy approximately is equal to 0. Hence when a light moving body collide against a massive body at rest and sticks to it, practically all of its kinetic energy is lost and there is no motion shown by that body. So what we have, if a light moving body collides against a massive target at rest and stick to it, all of its kinetic energy is lost in that case. Means both the bodies are remains at rest in such situation. So such type of collision is called perfectly inelastic collision. That's all about the perfectly inelastic collision, in which linear momentum remains conserved but kinetic energy is not conserved. There is some loss in kinetic energy. Final kinetic energy is less than initial kinetic energy, and the energy lost in the form of heat or sound. So that's all for the video. For further videos, stay tuned and keep studying. Thank you.